Hi folks! In the following video, our last one in the Substitution and Elimination chapter for alkyl halides, I'll be discussing predicting the products of substitution compared to elimination reactions. As a review, SN2 is a bimolecular substitution reaction that occurs in a single reaction step. Let's consider an alkyl bromide, in this case a chiral one, where the alpha carbon is chiral, and consider SH- as a nucleophile. In the SN2 mechanism, you bring a lone pair from the nucleophile to the alpha carbon and break the carbon halide bond in the same step. This forms your substitution product and a halide anion. SN2 reactions will always invert the stereochemistry of the alpha position. In this case, I showed this in my product by drawing the bond to the SH group as a dash instead of the wedge to bromine that was there starting out. The rate of SN2 reactions depends partially on the substitution of the alkyl halide. Methyl halides will react fastest, followed by primary, followed by secondary alkyl halides. And actually, these tertiary alkyl halides are totally unreactive in SN2 reactions. E2 mechanisms are bimolecular elimination reactions that occur in a single step. These involve a base and a carbon-hydrogen bond that is beta to the leaving group. The E2 mechanism involves three curved arrows. One from the base's lone pair to the hydrogen at the beta position. The carbon-hydrogen bond breaks and the electrons form a pi bond, and there's a loss of leaving group, all at the same time. The single step forms the alkene, the conjugate acid of your base, and a halide anion. E2 proceeds from an anti-periplanar conformation. The size of the base matters for E2 reactions. Small bases will favor the more substituted alkene product, whereas large bulky bases will favor less substituted alkene products. We'll always consider SN1 and E1 reactions together because they are competitive with each other. These are both unimolecular reactions that involve formation of a carbocation in the first step. Because a carbocation is formed, carbocation rearrangements can occur. An example of an SN1 and E1 reaction is below. Here I'm showing an alkyl bromide and water, a solvent that is a weak base and a weak nucleophile. There would be two SN1 products with different stereochemistries. To the planar carbocation intermediate, the water nucleophile could add from above, which would give a wedge OH group product, or the water nucleophile could add from below, giving rise to a dash OH group product. A third product that would be formed is an elimination product, an alkene. This forms from deprotonation of the beta position on the right that has hydrogens present on it. Rates of SN1 and E1 are opposite those of SN2. These rates would be exceptionally slow for a methyl halide, still really slow for a primary alkyl halide, and still really slow for a secondary alkyl halide. Typically, you're going to see tertiary alkyl halides or ones that are resonance stabilized. This trend in rates matches our stability trend for the carbocation intermediate. Often, in reactions with alkyl halides, more than one product will form. A skill to develop is the ability to predict all possible products that would form, and then to analyze all of those potential products and identify which one or ones are the major product. We'll do this using three steps. The first step is to determine the function of the reagent. Is it a nucleophile or is it a base, and how strong is it in those roles? Next, you'll want to analyze the alkyl halide substrate and determine, based on your reagent and your alkyl halide, what is the expected mechanism. After you've identified the most likely reactions and their mechanisms, you'll want to consider regiochemical and stereochemical outcomes and requirements. Regiochemical outcomes have to do with which constitutional isomer of product forms, and stereochemical outcomes have to do with either R and S stereochemistry or cis and trans or E and Z alkene isomerism. In step 1, you're going to be figuring out the function of the reagent. Is it a nucleophile or is it a base? Keep in mind that substitution reactions require nucleophiles, and eliminations require bases. I'm going to compare nucleophilicity to basicity. Nucleophilicity, essentially how strong a nucleophile is a kinetic parameter, having to do with how fast does that nucleophile attack the alkyl halide. How strong a nucleophile is a measure of how electron dense is it, and how accessible are those electrons to be donated during the nucleophilic attack. In contrast, basicity is a thermodynamic parameter. How stable are the reactants compared to the products of an equilibrium? And basicity measures how stable is electron density within a molecule. The more stable the electron density, the weaker the base. As an example, let's consider the bromide anion. Bromide is electron dense, and these electrons are readily accessible to be donated to form a new bond to an electrophile. So bromide is considered a strong nucleophile. If we're looking at basicity, though, the electron density of bromide is spread out over a large volume because bromide is large, so bromide is considered a weak base. You could also see this because it is the conjugate base of a very strong acid, with a pKa of -9. So this is just one example of a molecule that could be a very good nucleophile, but would be a very poor base. In terms of thinking about how the reagent will function, we'll want to consider different molecules and how strong or weak of a base are they, and how strong or weak of a nucleophile are they. In the category of molecules that are strong bases and yet they are weak nucleophiles, we have the following molecules. This hydrogen with a lone pair and a negative charge is known as a hydride. This molecule containing 2 nitrogens and a 5 and 6-membered ring is known as DBN. And this molecule containing a 7-membered ring and a 6-membered ring is known as DBU. These reagents, which are strong bases and poor nucleophiles, will typically favor reactions that go by an E2 mechanism. Some reagents are considered both strong bases and strong nucleophiles, and 3 such molecules are the hydroxide anion and alkoxides. These all feature anionic oxygens. Reagents in this category will favor either SN2 or E2 reactions, and which one is preferred depends on the structure of the alkyl halide. I'll be discussing this a bit later on in the video. Some reagents are weak bases, and yet they are strong nucleophiles. These include the iodide, bromide, and chloride anions, and sulfurs that are either negatively charged or neutral. These are halides, which hold negative charge really well, or they are sulfur, which is really large and spreads out the electron density over space really well. These reagents that are strong nucleophiles and weak bases will favor substitution reactions, but whether it's SN2 or SN1 depends on the alkyl halide structure. Our last category is reagents that are both weak bases and weak nucleophiles, and these will tend to be neutral solvent molecules involving OH bonds. Reagents that are weak bases or weak nucleophiles will favor the SN1 and E1 mechanisms. The next step for predicting the products formed is to analyze the alkyl halide substrate. Determine if it's primary, secondary, or tertiary. I'll first discuss the expected mechanisms for primary alkyl halides. For these substrates, the alpha carbon is very accessible to undergo nucleophilic attack. And primary carbocations that would be formed from these alkyl halide substrates are too unstable to form. With a primary alkyl halide, SN2 will occur if a strong nucleophile is used. E2 will occur if a strong base is used. And if you have a reagent that is both a strong nucleophile and a strong base, both SN2 and E2 products will form, but the SN2 substitution product will be the major one. Let's consider you had a case of a reagent that was a weak base and a strong nucleophile. An example of this is SH-. This would react with a primary alkyl halide to give exclusively the substitution product, and it would be formed by the SN2 mechanism. If instead you treated a primary alkyl halide with a reagent that is a strong base and a weak nucleophile, such as the hydride anion, you would get the elimination product as your sole product, and it would be formed by the E2 mechanism. If you treat a primary alkyl halide with a reagent that is both a strong base and a strong nucleophile, you'll get the substitution product as the major product, and it formed by the SN2 mechanism, but you will also form some of the alkene elimination product as the minor product, and it would be formed by the E2 mechanism. And last, if you treated a primary alkyl halide with a reagent that is both a weak base and a weak nucleophile, no reaction would occur. Now I want to consider our other extreme, the tertiary alkyl halide. The alpha carbon of a tertiary alkyl halide is very inaccessible due to the steric bulk of the carbon groups attached to that alpha carbon. And tertiary carbocations are stable enough to form in an SN1 or E1 mechanism. Tertiary alkyl halides will never undergo SN2 reactions, regardless of the nucleophile strength. But E2 elimination reactions will occur if a strong base is used. If instead a weak base is used, the SN1 and E1 mechanisms will occur. Let's consider a tertiary alkyl halide being treated with a weak base and strong nucleophile, such as a sulfur anion. In this case, the substitution product would form, and it would form by the SN1 mechanism only. If instead you treated the tertiary alkyl halide with a reagent that is a strong base but a weak nucleophile, the elimination product would form exclusively, and this would form by the E2 mechanism. If a tertiary alkyl halide is treated with a reagent that is a strong base and a strong nucleophile, such as an oxygen anion, elimination products will form, and they will form by the E2 mechanism. If instead the tertiary alkyl halide is treated with a reagent that is a weak base and a weak nucleophile, both substitution and elimination products will be observed, and they will be made by either the SN1 mechanism or the E1 mechanism. Last, let's consider the secondary alkyl halide, our intermediate substitution pattern. For secondary alkyl halides, the alpha carbon is somewhat accessible, but not super accessible. And secondary carbocations are typically too unstable to form. Secondary alkyl halides can undergo SN2 mechanisms if a strong nucleophile is used. They can undergo E2 mechanisms if a strong base is used. And if a reagent is a strong nucleophile and a strong base, the secondary alkyl halide will form products by both the SN2 and E2 mechanisms, but the E2 elimination product will be the major one. So, if the secondary alkyl halide is treated with a weak base, strong nucleophile, the substitution product is formed, and it's formed exclusively by the SN2 mechanism. If a strong base and weak nucleophile is used instead, the secondary alkyl halide will form the elimination products by the E2 mechanism instead. If a reagent is both a strong base and a strong nucleophile, both the elimination and the substitution product will be formed. The elimination product is the major one, and it's made by the E2 mechanism, and the substitution product is the minor product, and it's made by the SN2 mechanism. If a reagent is both a weak base and a weak nucleophile, it will typically not react with a secondary alkyl halide. The textbook has a really nice table summarizing these different predicted mechanisms for all of our different classes of bases and nucleophiles. I recommend taking a screenshot of this table from the textbook so that you can easily reference it later. And step 3 of predicting your products, after you've determined how your reagent is going to behave and the mechanism, is to consider the regiochemical and stereochemical outcomes for your different reaction pathways. I'm going to show these in a table. The regiochemical outcome for SN2 reactions is that the nucleophilic attack will always occur at the alpha carbon itself, the one attached to the halide. And the nucleophile comes into the backside of this alpha carbon, opposite the leaving group. The stereochemical outcome for SN2 is that an inversion of configuration takes place at the alpha carbon. The E2 reaction has the regiochemical outcomes depending on the size of the base used. The more substituted alkene product or products will be favored with a small base, and less substituted alkene products will be favored with a large base. E2 reactions can be described as either stereoselective or stereospecific, depending on how many alpha hydrogens there were at the position being deprotonated. E2 reactions are stereoselective in that they favor formation of trans over cis disubstituted alkenes. And they are stereospecific because they occur from an antiperiplanar geometry. In terms of the constitutional isomer of product formed for SN1 reactions, the nucleophile will attack wherever the carbocation is, and this could be multiple sites in the molecule if there is resonance. Also, the carbocation can potentially undergo rearrangement, which could give you even more possible regiochemical outcomes. In terms of stereochemistry, SN1 reactions form a planar and achiral carbocation, and then the nucleophile is equally likely to attack this from above or below. You'll end up with 50% inversion and 50% retention of stereochemistry at your alpha carbon. And this would result in a racemic mixture if your two products are enantiomers of each other. For E1 reactions, the more substituted alkene product is always favored because it is more stable. And these reactions can be stereoselective in that they favor formation of trans alkenes rather than cis alkenes. A new type of problem that we're going to be introducing more and more are what are known as synthesis problems. In these types of problems, you would be given a starting material and a product, and you'll want to choose what reagents will best get you to that product in the highest yield possible. The goal of synthesis in organic chemistry is to take simple molecules and make more complicated ones. And we'll do this by converting one functional group into another functional group. Let's consider two synthesis problems. One where you're starting out with this alkyl halide and trying to make the following alkene, or in the other case, you're starting with the same alkyl halide and trying to make a different alkene. Let's focus on the top alkene first. Notice that we've formed an alkene, so an elimination reaction has occurred. And for this alkyl halide, this elimination product is the less substituted alkene possibility. To form this product in the highest yield possible, you would want to use a bulky base to deprotonate the less sterically hindered position, the methyl group on the left side. This base would react with the alkyl halide by an E2 mechanism. The alkene shown on the bottom is disubstituted, and from this alkyl halide starting material we were given, if we want this alkene to form, we want the elimination to form the more substituted alkene possibility. To favor the formation of a more substituted alkene, you would want to use a small base, such as the hydride anion, and this would react with the starting alkyl halide by an E2 mechanism. Now let's consider we were given the following chiral alkyl halide, and we're trying to make the following product, where I have a new carbon-carbon bond formed to a CN group. Also notice that based on the stereochemistry as shown, the substitution reaction is occurring with an inversion of stereochemistry. To get the product I want, I would treat the alkyl chloride given with the cyanide nucleophile, and these would react by an SN2 mechanism, leading to the desired product. Last, let's consider we had an alkyl iodide, and I want to convert this into an alcohol. This reaction indicates that a substitution reaction has taken place. And notice that the alpha carbon is tertiary in this case. This means that I cannot have an SN2 reaction at this position, because SN2 reactions do not occur for tertiary alkyl halides. Instead of using hydroxide, an anionic nucleophile, I'm going to use water, which is a weak base and a weak nucleophile. Using water will promote an SN1 mechanism, which is allowed for tertiary alkyl halides, and this would give the substitution product that I want in the highest yield possible. If I had used hydroxide, which is a strong base, I would have gotten elimination products instead of the desired substitution product. So I had to be careful in choosing my reagent here. In summary, today's video talked about predicting products for substitution and elimination reactions. And to do this, you have to consider the function of your reagent. Is it a strong or weak nucleophile? Is it a strong or weak base? Then you need to consider the substitution of your alkyl halide. And then you need to consider the regiochemistry and stereochemistry of your reactions depending on their mechanisms. I also talked a little bit about synthesis and how you can use your reactant and product given to determine what reagent was added to your starting material. That's it for this video. I will see you in class.